Welcome back to Algebra 2. Today's lesson on Unit 6, Lesson 8 is on imaginary numbers. Now, up until this point, we have talked about a couple of different number systems. So just to give you a little bit of a reminder, back in kindergarten, first grade, we talked about the counting numbers, which means when you count 1, 2, 3, 4. So we have those counting numbers. So we call them the natural numbers. They're down here. That's like 1, 2, 3, and so on. All right. Bigger than the whole numbers, bigger than natural numbers, the whole numbers. The whole numbers are the same as the natural numbers, except this time we include 0, which is a really big deal. Okay, to be able to include 0 in our set of numbers. On top of the whole numbers now, we start including the integers. So actually, we denote that with a capital Z. And the integers are all the numbers on our number line. For example, -3, -2, -1, 0, 1, 2, 3. And of course, it goes on in both directions. And this is, I'm just trying to show you from here it goes to here, from here it goes to here. All right, now, larger than the integers are the rationals. And I know it's kind of funny to call it Q, but they're called Q rationals. And the rationals include every number that can be represented as a fraction. You can have also in there some non-terminating decimals, but they have to be repeating, like 0.33333. Repeating can be represented as 1/3. 0.666666 is 2/3. So you can also have repeating decimals in there too that are non-terminating. But all terminating decimals and non-terminating repeating decimals is represented in there. Now, the only one, this one does not sit on top of Q, it kind of sits next to it, and that's called the irrational numbers. And the irrational numbers are numbers that cannot be represented as a fraction. So they include numbers like, well, let's see this, we're going to call this one P over Q. Anything can be written as a fraction. This is anything like rad 2, right? Rad 3, rad 5, pi, the number e. These are all irrational numbers. And like I said, it doesn't, they together, the two of these create the real number system. And the real number system is basically every number that can be represented on the number line. So rational and irrational alike. But now there's one more that's on top of this. And I'm sorry, I didn't leave myself like enough room here. Let's see, can I do this? Of course not. Okay, so I just needed to group them. So basically, there is one more system above this, so I can move this down a little bit. Actually, I can move this up a little bit. And there's one on top of this that we call the complex number system, and it's like a capital C. And the complex number system contains and again, it's the real numbers together what's called the imaginary numbers. So together, they create the complex number system. Again, this is just supposed to be like a bold C. All right, like this is a bold R. So we're going to talk right now about what that imaginary number system looks like. So going back, in exercise 1, on the axis below, we have a sketch of y equals x squared. That's this one right here, y equals x squared. All right, so think about how the graph, this function now, f of x equals x squared plus 1. How is this graph, how is the graph of y equals x squared shifted to produce the graph of y equals f of x? Well, basically what happens is our graph that we have right here, if you have x plus 1, now you can get this very easily from your calculator as well. I don't want you to think that, this is magic here. But if this is your y-axis, basically what happens to our function is it gets shifted up just by 1. So this becomes y equals x squared plus 1. So it looks like this. So how does the graph y equals x squared shifted to produce? Okay, now don't use the word it. I'm going to say y equals x squared shifts vertically 1 unit. Okay, not a big proponent of the word it. So always make sure you're not using pronouns. You talk about what exactly you're talking about, because in this case, we've got two functions going on. We have f of x and we have y equals x squared. So C says, I'm sorry, B, we graphed that. C says, what can be said about the x-intercepts of the function y equals f of x? So I'm going to remind you that y equals f of x is our x squared plus 1 up here. So that's our blue function. So what can be said about the x-intercepts of this function? And I basically can say the x-intercepts for f of x do not exist in the real number system. I'm going to write that because you're going to find out that they do exist in the complex number system. So algebraically, show that these intercepts do not exist in the real number system. Gosh, I just wrote down exactly that. By solving the incomplete quadratic. So when you have an incomplete quadratic, it means that you don't have a b term or a linear term. So if we can solve this the same way we would solve a linear equation, by getting the x's to one side and the numbers to the other. So make sure, how do you undo x squared? Well, we take the square root of each side, and we get x equals plus and minus the square root of -1. So we know that because we cannot take the square root of a negative number in the real number system, that this does not exist. And on your calculator, you will get a do not exist or an error there. So since we cannot solve this equation using real numbers, we introduce a new one called the letter I. I is the square root of -1. So what we do is, when we simplify these, like in exercise 2, in terms of I can rewrite the square root of -9 as a real portion and an imaginary portion. So the real portion, the square root of 9, is 3, and the imaginary portion is I. And you can continue to do that with the rest of these, the real portion and the imaginary portion. Now, in this case, we're going to get a real portion that's going to have a radical in it, because the square root of 32 is the same thing as 16 rad 2 rad -1. So this becomes 4 rad 2. Now, we usually like to put the I mean, you have that -1 in the back, but generally how we like to have that I is we're going to move it right here, because that way we don't get it confused with that. And some people will write down, if you wrote this, you don't know if that I is under the radical or not under the radical. So we don't like to do that. We kind of think about it the same way with x's. Like if you're going to have x times 3, we don't usually write x times 3. We write 3x. All right, so it's the same type of thinking. So the last one here is rad 18, which is 9 times 2. So here's our real portion, and then here's our imaginary portion. So it becomes 3 rad 2, whoops, and the I has to go right there. So far, so good? All right, hope so. Moving on. Not there. So exercise 3 says, solve each of the following incomplete quadratics. Place your answers in simplest radical form. So we're going to solve these the same way we solved the other ones. So -8, 5x squared is equal to -20. Divide both sides by 5, and we get x squared is equal to -4. So that means x is equal to plus and minus. Sorry about that. Plus and minus, because what we did here is we take the square root of both sides. And when we take the square root, it's a plus and minus 2i. Moving on to B. you want to put your tracts in to help you stay organized, you can. So we get 1/2 x squared is equal to negative 18. Multiply both sides by positive 2. And I get x squared is equal to negative 36. Very nice that it's a perfect square. So x equals, take the square root of both sides again, square root, and x is equal to plus and minus 6i. Moving on to C. Remember, if I'm going too fast, pause. Subtract it again. Add 10. 2x squared is equal to negative 26. Divide by 2. X squared is equal to negative 13. And x is equal to plus and minus rad negative 13, which is going to be x is equal to plus and minus I rad 13. With that last one, it's the same thing. Even though the I is kind of behind it because we think about that negative 1, we pull it out front. And radical 13 can't be simplified any further. So we're going to spend a little bit of time in our next unit talking about multiplying and adding complex numbers. But I just wanted to show you an exercise 4, which is equivalent to 5i times 6i. This works the same way as if they were variables. All right. So, but the only thing is we can simplify it a little bit further with the I. So, in other words, if you had 5x times 6x, the answer would be 30x squared. So it's going to be kind of the same thing, but we're going to use i's this time. So 5i times 6i is equal to 30i squared. Now, I squared is equal to radical negative 1 squared. So they kind of undo each other, right? So what this does is this undoes this. So I squared is equal to negative 1. And that's kind of an important piece of information to remember, that I squared is equal to negative 1. So this is going to equal 30 times negative 1, which is negative 30. In exercise 5, it says from the pattern, I didn't show you the pattern, so that's an old exercise 4. What I wanted to show you about a pattern is, if you think of, you can do this right in your calculator, but I wanted to give you a little bit of a heads up on how to do this. So if you think about this, I to the 0 power, anything to the 0 power is 1. I to the first power is obviously I to the second power is equal to negative 1. We talked about that because it's negative 1 times the square root of negative 1 times the square root of negative 1, which is negative 1. And I to the third power would be I squared times I to the first, which is negative I. And when you get down to I to the fourth power, I to the fourth power is simply going to be, I think about it like this, I squared times I squared, which is negative 1 times negative 1, which is positive 1. Well, guess what? I to the fourth is the same thing as I to the 0. I to the fifth is the same thing as I to the first. I to the sixth is the same thing as I to the second. And I to the seventh is the same thing as I to the third. So I'm just going to erase this if I can get that eraser to work. All right. So these are all equal. So what you find out is whatever the remainder is when you divide by 4, that helps us. All right. So so for example, if I want to know what I to the 38th is, going to my exercise 5 now, I can say to myself, well, 38 divided by 4, it goes in 9 times, right, with a remainder of 2. Think about when you used to write division like this. With a remainder of 2, right, because it's 36 or 738, remainder 2. So remainder 2 means it's the same thing as I squared, and I squared is negative 1. 21 divided by 4 is 20. This time it has a remainder of 1. So this is the same thing as I to the first power, which is simply I. 83 divided by 4 goes in goes in with no times 20 with a remainder of 3. So it goes in 20 times, which is 80, with a remainder of 3. So a remainder of 3 means it's going to be negative I, because you're going to use this one right here. And 40 goes in evenly, right? So if you do 40 divided by 4, this equals 10 with a remainder of 0. So anything to the 0 power is 1. Now, if you didn't get that whole thing, believe me, you can use your calculator. So let me just show you quickly on your calculator, down here at the bottom where the pi is, all right, hit that pi. Mine's having a little bit of an attack here. And right next to the pi is the I. So I. So if you want to do some of these to this power, if you look and see that we just have I to the 83rd power, so I'm going to raise it, use my little caret there, raise to the 83rd power, you get an answer, which is negative I, which we said that was the answer. The last one said I to the 40th. So pi I raised to the 40th gets me 1. So your calculator will do it for you. So we're not going to make a big deal about learning how to do this by hand. So using our calculator makes this so much easier without having to think about how to do it by hand. Because when you took a look at exercise 6 and you see this mess right here, well, back in my day, we had to do this all by hand, but your calculator will do it for you. So if you take a look at that exercise, 5I to the 16th power. So 5I raised to the 16th, hit the side button to come back down, plus 3I raised to the 23rd power, side buttons come back down, plus I raised to the 26th power. Did I do it right? 5I to the 16th plus 3I to the 23rd plus I. Yes, always take a minute and just take a look at it and hit the enter button. And there's your answer. 4 minus 3I is your answer. So when you come back here, 4 minus 3I is sitting right here. So if you get a question like that, that's like, here's your 2 points served on a silver platter. All right, so you're going to spend some more time doing these, probably in class, because I would like you to have access to your calculator when you're doing these. All right, so that's it for today. 17 minutes, cool beans. And as I always say, please always make good choices, all right, every day. I'll see you next time.